sort of review of stellar elemental processes happening around massive black holes. In particular, focusing on the non-spherical galactic nuclei. Non-spherical means either flattened or even triaxial. I can make a clear distinction between the cases later on. So first, just remind what do I mean, what do we mean by processes which lead to capture or tidal disruption of stars. And then I'll devote a certain fraction of the talk discussing how the orbits around the black holes look in the non-spherical case, and underline the differences between the spherical, axisymmetric, and triaxial nuclei, or nuclear shock clusters, that are usually interchanging. Then I'll go on to discussing the two-body relaxation phenomenon, again in the nuclear star clusters, because these are the effects which ultimately lead to the capture of stars. And in particular, I will be underlying the differences between the emptyfull regimes, both in spherical and non-spherical cases. And that will lead me to the discussion of postcon draining versus relaxation. That effect is, these two distinctions are important only in the non-spherical cases. And then I'll really come to the predictions for realistic galaxies, although we won't speak that much more. So the whole idea of the talk would be to discuss how the stars manage to get into the black hole. And I will be using this the concept of the Love's cone. The term originally I think was derived in plasma physics, but it was also adopted in the astrophysics, describing the so-called cone in the velocity space from which a star can get into the black hole. So what do I mean by that? Here I plotted the trajectory of a star which eventually ends up being disrupted or even maybe captured by the black hole when passing at a small enough distance from the black hole. And at any given point in space, there is a certain region in the velocity space, a certain region in the direction of the velocity, from where the stars will actually enter the tidal disruption radius. So if the velocity at this point was directed within this cone, then in order to lead the star to a small enough radius from the black hole, so that it will eventually be captured. So that cone means actually a cone in the velocity space, but I will not be using it in this sense, because I will be dealing with the phase space in terms of energy and momentum or some other integrals of motion, but the origin of the term is here in the velocity space. So the radius at which the star is getting into the black hole, it may be either just a few times faster the radius, the minimum radius of approach at which this orbit eventually ends up spiraling into the black hole for the test particle, for the point mass, or for a star of finite mass, it would be a somewhat larger radius at which the star is being tidally disrupted. So I will denote this radius and corresponding angular momentum as L some large dipole. So it is either the radius of the angular momentum of the closest possible approach for a point mass, or a larger angular momentum corresponding to the tidal disruption. And actually, what happens to the star depends on the mass of the black hole and on the side of the horizon. For large black holes of larger than 10 solar masses, most of the stars end up just plunging into the black hole without being disrupted. For small black holes, the star of a solar mass and the main sequence star, not the compact star, would be disrupted before entering the black hole. But I'm not really concerned what happens to the star after it gets too close to the black hole. My point is how to make the stars get there, not what happens after it. Okay, so I will be discussing the nuclear star clusters or galactic nuclei, and obviously, since I'm speaking about the supermassive black holes, there is a component of potential which is created by the black hole itself. I will not discuss any relativistic effects in this talk, so the black hole just creates a standard Newtonian potential, and then there is additionally a distributed mass in form of the stellar cluster. So that distributed mass of the stellar cluster is often assumed to be a power law density profile radius with the exponent gamma. So that is the total gravitational potential, which is the sum of the two parent term plus the term from the stellar potential. And since I will be focusing on the non-spherical cases, so it's not only the spherical term, but also I include additional terms which are non-spherical. For example, if I only consider these two terms, that means that I'm considering flattened systems, axisymmetric systems, which are have equal radius in x and y direction, but different in z direction. And if I include this term as well, then I will be speaking about triaxial systems. But these coefficients here are assumed to be moderate or small, epsilon and theta. These are coefficients of flattening. So since most part of the talk will be devoted to considering the motion of stars which are close enough to the black hole, so that this first term actually dominates the total potential. That means that we are dealing with the radii which are smaller than the influence radius, which is customarily defined as the radius, so that the stellar mass within this radius is twice as large or comparable to the black hole mass. And since this term will be dominant in the potential, the orbits of stars will look in the zeroth approximation as Keplerian ellipses. And then the first correction to this would be an ellipse which is not closed, but it is actually precessing. So in the essence of the stellar potential, it would be just closed Keplerian ellipses. And these additional terms create precession. Since these terms are smaller comparable to the first term, obviously the precession time scale will be long compared to the regular time scale, which means some different simplification after all. So I will just show how the precessing orbit look like. So that is the dot marks the position of the black hole, and that is the ellipse in three projections. And so the star is moving, for example, in this direction, and I'll be plotting its evolution for a longer time scale. So this is the three projection of actual orbit of a star in a slightly triaxial nuclear cluster. So the orbit is on the short time scale, it is like moving in the ellipse. On the longer time scales, this ellipse itself is precessing in some plane, so it feels like sort of an annulus. On even longer time scales, the annulus plane itself is also precessing, changing its orientation. So in total, what we end up with is some sort of torus, some kind of object with an inner hole, and then it looks like a bottom. And then in this manner, I call the evolution of angular momentum of the star. So indeed it experiences some kind of oscillations. So these are standard type of tube orbits which exist in all non-spherical systems. Axisymmetric or triaxial doesn't really matter. But there is additional sort of orbits which are called pyramid orbits, which only exist in triaxial systems. So again, these are Keplerian ellipses, but instead of precessing all the way in the same direction, you see in this way, it actually precesses one way, then it can be, then it can be reflected and not continue all the way there. It's actually precessing in some sort of figure of weight or whatever. So in this case, the orbit does not have any predefined sense of rotation. And for those of you who know thermodynamics, this is the analog of box orbits, which are exist in any triaxial systems. But what is specific for the motion around the black hole is that these orbits, they actually don't look like boxes, but they look like pyramids. So that the black hole is at the pinnacle of the pyramid. Why these orbits are important you can see it from this plot, which is again the angular momentum. But now you see that the oscillations in angular momentum are really large, and more importantly, you can get arbitrarily close to zero. So in this axis, this is the angular momentum, and then, while performing these kind of oscillations, the orbit actually can attain arbitrarily low values of angular momentum.
So they only exist in the presence of a black hole?
Yes. Without the black hole, there is a class of box orbits which have the same property of getting arbitrarily close to the origin. For the black hole case, I may say that actually this is the orbit which originates, which is when the angular momentum goes to zero. That means that the orbit is actually degenerates to a line. So that will be a line, and one end is at the black hole, and the other end is at one of the corners of the pyramid. So here is maybe this better idea to begin by looking into the projections of these orbits. So cube orbits, they look like donuts, and the pyramid orbit looks like the pyramid. It's not like it's not a perfect pyramid, of course, but looks like a pyramid. And there is also a subclass of cube orbits which are called saucers, which are also which also have a predefined sense of circulation, but they have slightly different shape. These orbits are actually important in the following discussion, because in the axisymmetric case, most of the capture rate of most of the stars going into the black hole originate from the saucer orbits. And in the triaxial case, as I'm trying to explain, the pyramid orbits could be more important because they can attain arbitrary low values of angular momentum, which means essentially that you can hit the black hole at any point in their life. Yeah, so that summarizes what I was explaining before. Again, I write down the potential, and I make the point that we have a clear separation of time scales. The radial period, the clear expression for the radial period, is much shorter than the precession time scale. So basically, the precession time scale is longer by a factor which is black hole mass over the stellar mass of the given radius. So if you get close to the black hole, then the precession period is much longer than the radial period. And this separation of time scales actually allows to make a certainty, which I will not explain in detail, but this basically means that we have we can do involving an adiabatic approximation and average the motion over the radial period to obtain the evolution of the orbital elements, or the direction of the angular momentum vector and the direction of the eccentricity vector, which describe the shape of an orbit. Essentially, they are separating the motion into two elements. One is the motion around the within one there in the ellipse itself, and the other, much slower motion, is the changing of the parameters of this ellipse. And another thing which may be not very obvious is that in both axisymmetric and triaxial systems, the motion described by this kind of averaging procedure is completely integrable. You have one integral portion which is energy, which always exists in systems which are in which the potential does not depend on time. And we are considering, of course, the systems which are, let's say, quasi-stationary, in which potential does not change or appreciable for time scale. Then there is another integral portion which is obtained by this energy procedure. And then in the axisymmetric case, we have an obvious integral portion which is z component of angular momentum. In the triaxial case, there is another integral which is related to that. So the motion is completely integrable, which actually does not happen all the time in systems which are far from being spherical. But in this case, it does happen. So what happens to the angular momentum then? As I showed, the angular momentum experiences some sort of oscillations. In the axisymmetric case, of course, there will be only one frequency of the oscillation. In the triaxial case, there will be two frequencies, so you see like sort of beats, interference pattern. But what does matter is that, for example, this is a similar plot that I was showing in the movie. This is the plot of how angular momentum changes for pyramid orbits. So you see that it can actually hit very low values and can go all the way down to zero. For tube orbits, it is not the case because tube orbits have some mean value of angular momentum, and then there is a range of oscillation, but the range doesn't go all the way down to zero.
So is that the one that actually goes down to zero? Is that actually regular? Or?
It is regular, yes. It may not be so obvious from here, but actually this is a sum of two sines, or the two harmonic functions. So for any orbit, we can define the minimum and maximum value of angular momentum. The quantity r stands just for the square angular momentum is not really angular momentum squared. And if the minimum value of angular momentum is low enough, if it is lower than the capture, the critical value for capturing, then of course the orbit is of interest for us because we can get into the black hole. So what happens to such stars which can actually enter the black hole? We can call this region of phase space an extended loss cone or extended loss region. So as I told in the spherical case, the loss cone is defined as the region in phase space for which angular momentum is lower than the capture boundary. In the non-spherical case, we have the angular momentum of individual stars oscillating back and forth between some minimum and maximum value. So the loss cone will be that region in phase space for which the minimum value of angular momentum is below the capture boundary. Right? So since the angular momentum is allowed to oscillate, then obviously there are more orbits in this extended region than in just the spherical loss cone. In that sense, we can actually get a lot more stars into the black hole. But a lot more doesn't mean that it is enough. And I will explain why. But before I go there, just make a remark that, again, stressing that in the axisymmetric case, the condition of being in this loss region implies that first, the z component of angular momentum should be below the capture boundary, because this is a quantity which is conserved. And then the second condition is that the other integral of motion should be less than certain threshold. Or, stated differently, that the mean value of angular momentum should be less than that quantity which I defined earlier, which is linked to the flattening of the potential. So that may be a small quantity, but it is much larger than the size of the loss cone. Just to make an idea of what numbers I'm speaking of, the size of the loss cone or the ratio of critical angular momentum to the angular momentum of circular orbit, maybe like 10 to minus 6 or so. This is roughly the size of the capture radius or Schwarzschild radius of the black hole to the radius of an orbit. For example, for nuclei black hole, the Schwarzschild radius is like 10 to minus 6 parsec, and the typical sizes of the black of the orbits in the sphere is about 1 parsec. So that's like 10 to minus 6. But this quantity, even if it is smaller, it may be like 0.1 or so. So in this sense, we are getting much more orbits which can actually enter the loss cone. And for triaxial systems, as I mentioned, all the pyramid orbits are subject to being captured at some point in their life. So the entire this much of the phase space is actually on the centrophilic orbits. Centrophilic means that they can have very close to the origin. So to compare the three cases, I want to take a sort of chart here. In the direction of decreasing symmetry, we have increasing number of stars in this loss region. So for spherical systems, it's just the size of the loss cone. For triaxial systems, as I told you, this is a fraction of order unity independent of the size of the loss cone. Axisymmetric systems are somewhere in between. But for any orbit in this loss region, the chances of getting into the black hole actually decrease proportionally. In the sense that for a spherical system, once you get the angular momentum below the capture boundary, then the orbit, the star gets into the black hole within one radial period. For a triaxial system, it takes much longer. It may take longer than half the time. Again, the axisymmetric systems are somewhere in between, and for them, this time scale, lifetime of stars in the lost region orbits is for the precession time, or 5 to 6 years. So in order of decreasing degree of symmetry, we have increasing number of stars in the lost region and also increasing the lifetime of the stars in this region. So of course then we may ask the question, what happens when the stars in this region are all drained, captured by a black hole, so that the entire region of the phase space which is in the lost region is empty. Then of course the stars can still get there, but on the time scale of relaxation time. The standard definition of the relaxation time is relates to the Watson dispersion and the density of stars. And for galactic nuclei, the relaxation time is typically longer than the Hubble time. Only for small galaxies, or not necessarily small, but at least dense galaxies, galactic nuclei like Milky Way, this time may be for the Hubble time. For giant elliptical galaxies, it could be like 10 to 15 years or more. So that time scale is clearly much larger than the precession time scale I defined earlier. And that may be even larger than the lifetime of the pyramid orbits in the triaxial case. So if we get back to the spherical case, again I repeat the definition of the lost column. This is the region from which a star would be captured within one radial period if its angular momentum did not change.
That's so that formula gives the time scale for diffusion in energy.
It could happen faster because of the resonant relaxation, right? But yeah, that is the standard definition of time scale for diffusion in energy. For angular momentum, it would be somewhat faster. But still, it would be much slower, much longer time scale than the precession time. So, again, even for the spherical system, things are not so trivial, because they have actually two time scales. One is the radial period itself, and the other is the time scale during which the relaxation, the jittering of the angular momentum because of the relaxation, changes the angular momentum by order of the capture boundary. So, so if you plot angular momentum, square versus time, if you have a spherical system and if there is no relaxation, of course it will be constant, right? It's not. Here I plot some which will be the capture boundary. Can you see that? For again, still for the spherical case, but if we now turn on the relaxation, then the angular momentum is jittering somehow. It's a random walk. It's a random process, so the angular momentum is changing somehow. It can go below the capture boundary, it can go above, and the typical time scale for which it stays below the capture boundary may be comparable, maybe it's lower, maybe higher than the radial period. So there are two time scales which come into the computation. And in the non-spherical case, you will have the regular precession, and on top of that, you will have the relaxation. So we'll come to that. But before coming there, I will tell you this quantity, which is the ratio of the two time scales. One is the typical time scale for changing angular momentum because of the relaxation. The other is the radial period. Why is it important? Because imagine that you have emptied the entire lost column. Then what something, but I don't know if you really see it. But anyway, so that's essentially the same figure I was trying to draw on the board. Here I plotted the ensemble of stars, distributed sometimes angular momentum. This is the capture boundary, horizontal axis is time. And I marked the orbital, the radial periods the lines. So at first, we start with no stars being inside the lost cone, no stars having angular momentum smaller than the capture boundary. Then, because of the relaxation, stars keep diffusing there, but in the one regime, the relaxation is slow enough that the star barely managed to get into the lost cone before being captured at the very center. So again, I remind you that the lost cone concept is defined in terms of the angular momentum, but the actual capture of the star by the black hole happens only when the star goes to the very center. So, for example, if the star's angular momentum was low at the apocenter, but then somehow it changes before it has reached the very center, then it can get out of the lost cone. That's fine. The star will escape capture. But if the angular momentum changes slowly, then it only can barely hit there, and then it will be captured within one radial period. In the other case, when the relaxation is really fast, we see that the stars they can get in and out of the lost cone very efficiently. So basically, most of the time, the lost cone keeps being full. The density of stars here in this region is the same as everywhere. Only at the very center passage, the lost cone is empty, but then again it is refused very quickly. So in that case, the density of stars here is more or less the same as outside the lost cone. So of course, that depends on the radius of an orbit. If the star is close to the black hole, then the radial period is very short. So in that case, the star will be in the empty lost cone region. Far from the black hole, it will be the full lost cone region. Again, for realistic cases, for example, for Milky Way, the transition between these two regimes happens roughly at the radius of impulse. That is at several parsecs. The radius of the orbit. For giant galaxies, like M87 or whatever, or giant elliptical galaxies where black holes can be 10 to 8, 10 to 9 solar masses, then these galaxies are essentially all of them are in the empty lost cone region for the spherical problem. So why is this important? First of all, this defines the boundary condition for the entire diffusion problem, because that relates the number of stars captured per unit time to the density of stars close to the black hole, to the capture boundary. But for the spherical case, that also defines the entire profile of the stellar distribution function. So here I plotted a standard result from 70, which was result for spherical symmetric stellar clusters, and we get black holes, only hypothetical at that time, which also applies essentially unchanged to the spherical galactic. So that is the distribution of stars, the number of stars at given angular momentum. Isotropic distribution would mean that this is a constant. Since we have the capture boundary, stars with a small enough angular momentum are captured, then we, of course, we expect this distribution function to be slightly depleted, or maybe substantially depleted at low angular momentum. And the empty and full lost cone regimes differ from each other by how much is it depleted. So for the empty lost cone regime, essentially the distribution function goes to 0 at the capture boundary. And the slope of the distribution function, the gradient of it, is determined by the efficiency of the diffusion. So the flux of the stars into the black hole, or the capture rate per unit time, is determined by the gradient of the distribution function. On the other hand, in the full lost cone regime, this distribution is almost flat. It is slightly depleted, or very close to isotropic. So the capture rate is just the size of this lost cone divided by the radial period. As I told you, all the stars which manage to diffuse into the lost cone are within one radial period. So in that case, the capture rate does not depend on the diffusion coefficients. So it is determined just by the size of the lost cone. And overall, the solution of the distribution function is described by logarithm plus constant. And in the empty lost cone regime, this is the coefficient at the logarithm, which is important, the slope of the distribution function, which is important. In the closed cone regime, it's just the normalization which is important, because the slope doesn't matter. So that was a review of the spherical problem. Now I come to the non-spherical galaxy. What changes in that case? In that case, as I told you, there is it's not only the lost cone which matters, but actually a much larger region of the phase space from where stars can get captured. But the lifetime of the stars in this region is also increased. And in the triaxial case, it may be increased beyond the half time. So the lifetime of the stars in the lost cone, I denote it as the draining time, the lost cone draining, lost region draining. If we are speaking about times much smaller than that, then basically we don't need to invoke any relaxation. We just have the constant flux of stars into the black hole from these centrophilic orbits. This is essentially the case for triaxial systems, but it is also for axisymmetric systems. If you are speaking about times which are longer than the draining time, then we come to the similar situation to the spherical case. That is, we have a sort of lost region, and the capture rate is determined by how fast stars can diffuse into this lost region. So in that sense, we are limited by the relaxation. And the reason why we expect the capture rates to be higher in the non-spherical case, obviously because the lost region is larger. So for example, if we compare it to the spherical case, this is we have plotted the solution of two-dimensional equation. I'm not going to details how did we solve it, but that's basically numerical solution of two-dimensional quantum equation. For comparison, I plotted the same solution for a spherical system. So for large angular momentum, the stars do not know about the larger size of the lost cone. They just do not feel that something is wrong happening with the low angular momentum stars. So the diffusion rates here are essentially the same as in the spherical case. But at the low angular momentum, the distribution function of stars is modified with respect to spherical case in such a way that equivalent spherical system would have just a larger lost cone capture boundary. So we have still this kind of logarithmic profile for the solution, but the size of lost boundary in the non-spherical case would be larger. But since the flux depends on the size of the lost cone on the logarithmically, that means that we do expect an increase in the capture rates, but we don't expect it to be very dramatic. It would be a factor of few. And it would only be relevant for the cases where the entire process is diffusion liquid. If you go back here, in the closed cone regime, we won't see any difference because the distribution function is flat anyway. So the capture rate is just by the size of the lost cone of the capture boundary. So the difference between capture rates in the spherical and non-spherical systems is like this. Obviously, in the non-spherical cases, the capture rates will be higher, but not dramatically higher. Factor of few. If the diffusion if the entire process is diffusion. For the triaxial systems, as I noted, we may still not be in this region because we still have the draining of the pyramid orbits. The draining timescale for pyramid orbits will be larger than the Hubble time. In that sense, we are not, in that case, we are not limited by the relaxation. It will be just the capture rate which follows from the draining of the pyramid orbits.
Diffusion limited when you are in the end velocity.
Sorry, what?
diffusion limited, you mean, in the glass conducting?
Yes. Diffusion limited means that the capture rate is determined by the gradient of by the slope of the distribution.
Because I didn't get the logic. So, but the gradient of that depends on sink.
Yes, it depends.
So,
yes.
but now you're saying also the gradient of that determines the loss rate, which is true.
Mm-hmm.
But surely you change the sink. Well, the two are interdependent.
Yes. What I'm saying is that it does not depend on it dramatically. It depends on the size of this scene. So, okay. I have two cases. One would be the spherical case, for which we have just no small boundary, and the other would be axisymmetric case, for which we have a much larger effective no small boundary here. This quantity may be much larger than this one, but since the overall solution is logarithmically depends on it, the actual slope or equivalently the capture rate would increase moderately, factor of u at most.
Just to make sure I understand, so when you say it's triaxial, you've had two parameters, an eta and an epsilon.
Mm-hmm.
You're saying they're comparable. I mean, does this depend on how triaxial
Well,
they are? I mean, presumably if you take that eta to zero, it's the other case. So how triaxial do you need to be for the triaxial case to apply? I guess.
Yes, in some sense, of course, axisymmetric case is the limiting case of triaxial systems, right? So if the system is substantially triaxial, in the sense that the intermediate axis is somewhere halfway between the major and minor axis, then the pyramid orbits would comprise substantial fraction of the axis. If the system is very close to being axisymmetric, then there is probably a smooth transition to the axisymmetric case, in the sense that the pyramid orbits do exist, but they are very small and they will be drained very quickly. So that again you get into the
It's sort of linear dependent. So if you have sort of half of eta is half of epsilon, so you have
yes. So yeah, if eta is somewhere between 0 and epsilon, and not very close to 0, not very close to epsilon, then the system is substantially triaxial. I think now I come to the conclusions. And again, a few points to underline here. In the non-spherical cases, the angular momentum itself changes both because of the two-body relaxation and because of the regular recession in the smooth potential of the stellar quantum. And since we have two sources of changing angular momentum, we can capture the stars more efficiently. Basically, the stars can be captured from a region of phase space which is much larger than the standard telescope. You only need to have the minimum rate of angular momentum below the capture boundary at some point in the recession zone. And we have two competing two separate effects. One is the loss draining, which always happens at small times. But then later on, when the loss has been drained, it has been gone. Then the capture rate is determined by relaxation. For triaxial systems, the relaxation might be not very important because they are still in the loss draining region. For axisymmetric systems, the draining time is small, but in the relaxation regime, the difference between capture rates in the axisymmetric and spherical case may be moderate. For the analyticals, all these considerations are even more important because the analyticals are always in the emptyfull regime. So any departure from spherical symmetry would be more important for these calculations. And the astrophysical applications would be, of course, everything which depends on how often can you make things come close to the black hole. That would be random disruption events of stars. That could be extreme mass ratio in spirals. Here we mentioned the compact object of different black hole, close to the supermassive black hole. The same effects are important for the evolution of binary black holes, for the reasons that I got detailed here, but that is basically the binary black hole. In order for it to shrink, we need a supply of stars which can interact with the binary. And that essentially is similar to the Bose-Cone problem, but the Bose-Cone is the radius of importance is the binary separation. If you manage to get orbits close enough to the binary, then there is a three-body scattering process which ejects the incoming star with higher energy, and the binary is able to shrink. So if there are no stars which can interact with the binary, then the binary just stops. So this process will enhance the rate of interaction of field stars with the binary and enhance the rate of coalescence of the binary. That is the project that I'm doing the study. And yeah, everything else you basically mentioned about getting stars or something has to do with black hole. Thank you.
How optimistic are you that you can get supermassive black hole binaries to emerge purely or mainly by interacting with stars rather than gas?
So that's essentially, I didn't mention here, that's the essence of the final parsec problem. That in the standard scenario, the rate of interaction of stars with the binary drops down to zero after some time, and then basically you cannot reverse the black hole because of this thermodynamic process. But any departure from the spherical symmetry will enhance this rate, and most likely you will end up merging the black holes within the half time of interaction. So that is one of the processes which will help to actually parse the problem.
Doesn't that depend on how triaxial it is?
It does, yes.
How
it does.
is it that for the system to see out there? Is it, do you have enough information to know?
Well, I don't think we have that many systems in which we can, observationally, we don't have that many galaxies from which we are sure of the existence of two black holes. Not only of the existence of the two black holes, but actually black holes had small enough separation that the whole final parsec problem is important. So, it would be likely relevant to these systems because if the galaxies merge, then the merger remnant does not need to be spherical symmetry. Most likely it will be flattened or triaxial or whatever. So in that case,
When you deal with the merger of very massive black holes, and massive black holes, how good an approximation is it to assume that you have a certain amount of triaxial? I know this is a bit off your topic, but that's, according to things I do. How good approximation is it to assume that you have a given triaxiality in your galaxy, and there's no feedback of this, very massive perturbation on the stellar distribution?
That's a topic which I think has not been explored so far. We are trying to address it. But of course, it's maybe not very fair to assume that there is a fixed background of stars, of given flattening triaxiality, and then there is just two black holes moving in the background. Of course, there will be something there. For example, there is a paper by Hendrock and co-authors about 10 years ago, which was considering these binary black holes which steer the population of stars, we check the galactic layers in the terms.
Create core and so on.
Yes, okay. That is, I cannot answer technically on this question.
You mentioned relativistic effects a few times. I mean, are they actually important at all? Or,
they are. It is interesting that for these pyramid orbits, since they can get to a very low values of angular momentum, that means that the reduced precession can actually take over the precession from the distributed mass. some precession.
Does that tend to lower?
That tend up to limit their possibility of getting to the black hole. So essentially, only the pyramid orbits in a certain range of radii can get into the black hole. Pyramid orbits which are very close to the black hole, they will never look like this.
I have a last question. So in standard theories, most of the flux, like in galaxies, I think really comes from the influence radius of the supermassive slightly outside. While the other pyramid orbits are well inside the influence radius. I was wondering how the flux from stars, at least the eye, compares to the flux from stars in the pyramid orbit.
I think, well, the pyramid orbits they exist all the way up to the influence radius from the side of the unit. And actually most of the flux comes from around the influence radius as well. Just because there are more stars in this radius. Sorry, that's my comparable.
So we will take...
There's someone behind you.
Oh, sorry.
What determines, you have pyramid orbits, but you also have orbits so it's just the initial conditions that determine which of those orbits you're on.
Well, what kind of orbit?
I guess what I want to know is how do you know what fraction of stars, real actual galaxies will be on pyramid orbits?
Yes.
Because just because that kind of orbit exists doesn't mean that there will be stars on it, right?
Right, but if we just take any sprinkle the stars isotropically in the background potential and follow the orbits of all of these stars, we see that a certain fraction of them end up being on pyramid orbits, and that fraction depends on the flattening of the potential. And if you see the stars randomly in the space and in the velocity, then there is a well-defined fraction of pyramid orbits. But it doesn't mean that in the real case there will be the same fraction, because these points can be different.
So if you formed a galactic nucleus by having a merger with other galaxies, then would be like to get lots of information because you would essentially be sprinkling lights isotropically?
Yes, I think that, yeah. Yes. Any mechanism which creates stars more or less without any preferred dominance of circular or radial motion, then more or less there is a lot of fraction.
Other questions? Okay, let's thank Eugene again. The cookies upstairs, tonight we're taking